In 1961, a meteorologist at MIT rounded 0.506127 down to 0.506. It was a mistake that changed everything. Edward Lorenz was running a weather simulation on a computer the size of a refrigerator. He wanted to rerun a section, so he typed in the numbers from the printout. But the printout only showed 3 decimal places, 0.506. The computer's memory held 0.506127. He didn't think it mattered. It was 3 millionths. That's like leaving a single grain of sand out of a sandcastle. He went to get coffee. When he came back, the weather had completely changed. The forecast diverged. Storms appeared where there had been sun. The simulation had gone rogue. Lorenz didn't find a bug. He found a law of nature. The tiniest possible change in the starting conditions made the long-term future completely unknowable. This is the real butterfly effect. Not a butterfly causing a tornado. That's a myth. The real story is about a rounding error. Think of it like this: a toaster. You set your toaster dial to 2.5. Tomorrow, you set it to 2.5001. You can't feel the difference. The knob looks identical, but one gives you light toast, the other gives you charcoal. Weather is the same, but with a billion invisible notches. And you can never set it exactly right. That's the problem. Not bad data, not lazy meteorologists. The math itself walls off the future. So what is this thing? It's called deterministic chaos, and the name is a trap. Chaos sounds like randomness. It's not. Random means no rules, a dice roll. You can't predict it because it's genuinely chance-based. Chaos means rules, perfect, rigid mathematical rules. You just can't predict it anyway. The system is deterministic. Same inputs always give the same outputs, but the inputs are never exactly the same, and the differences explode. A double pendulum is chaotic, no dice inside, just physics, but swing it once. Then swing it again, with your hand a millimeter to the left. Within seconds, the motion is completely different. That's the nightmare. The system is lawful, but it's also a traitor. It takes your tiny ignorance and inflates it until your forecast is garbage. Lorenz didn't just name the problem. He drew its portrait. In 1963, he published a paper with 3 simple equations. They modeled a simplified atmosphere, convection in a fluid layer. The equations were short. You could write them on a napkin, but their behavior was infinite. When you plot the system's state over time, it traces a shape, a beautiful, looping, never-repeating shape, the Lorenz attractor. It looks like a pair of butterfly wings. That's not a coincidence. The shape is a fractal, infinite detail at every scale. The trajectory spirals around one wing, then flips to the other, then back. It never crosses itself. It never settles. It never flies off to infinity. It's bounded, trapped, but completely unpredictable. That's the face of chaos. A system stuck in a box, but never boring. So where did the butterfly come from? In 1972, Lorenz gave a talk. The title was a question. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? He didn't say yes. He was asking if the atmosphere was so sensitive that a tiny flap could cascade into a storm weeks later. The answer is no, not in a literal, traceable way. The butterfly flap is a metaphor, a poetically precise image for sensitive dependence. The public heard the title, skipped the question mark, and invented a causal chain. Butterfly flaps wings, air moves, chain reaction, tornado. That's not how it works. The flap's energy dissipates. It gets swamped by everything else. The butterfly doesn't cause the tornado. The math causes the unpredictability. The butterfly is just a mascot, a very famous, very misunderstood mascot. So if the butterfly isn't the culprit, what actually limits prediction? The answer is a number, a Lyapunov exponent. It measures how fast chaos grows. Imagine 2 starting points, microscopically close. The Lyapunov exponent tells you how quickly they fly apart. Positive exponent means chaos. The bigger the number, the faster you lose the future. For weather, that number gives you about 2 weeks. Not because we lack data, not because computers are slow, because the math has a built-in expiration date. Beyond that horizon, the errors are bigger than the signal. You're not forecasting. You're guessing, and here's where it gets worse. Lorenz didn't stop in 1963. In 1969, he wrote another paper. This time, he looked at a different kind of model. Linear, but with many scales of motion. Big eddies, small eddies, tiny eddies, all interacting. And he found the same wall. Predictability dies, not from nonlinear feedback this time, from the sheer cascade of scales. Energy flows from big to small. Errors at the tiny scales infect the big ones. It's a different mathematical mechanism. Same result. In 2023, a team led by Shen re-examined both models. They presented at the Chaos Conference in Heraklion. Their finding? The limits come from distinct mathematical structures. 1963 is nonlinear sensitivity. 1969 is multi-scale contamination. 2 different roads to the same cliff. This isn't a temporary technological shortcoming. It's a feature of the system. Richard Anths, writing in National Geographic in 2025, put it bluntly. Atmospheric prediction is limited to a few weeks. Not due to lack of data, due to the mathematical structure of the system. You can't outdata the problem. You can't outcompute the problem. The system itself says no. So what do? Do we just give up? No, we cheat. We change the question. Weather is an initial condition problem. You need to know exactly what the atmosphere is doing right now. Chaos eats that. Climate is a boundary value problem. You're not asking about next Tuesday. You're asking about the average of the next 30 Tuesdays. The chaos averages out. The forced trends remain. Carbon dioxide goes up. The planet warms. That's not a weather prediction. That's a physics prediction. It's like a river. You can't predict where a single leaf will be in 10 minutes, but you can predict the river will reach the sea. Climate models use ensembles. They run the same model dozens of times with slightly different starting conditions. The individual runs diverge, but the envelope of possibilities stays meaningful. That's how we know the planet is warming, not by predicting a single day, by predicting the shape of the whole cloud. Chaos doesn't defeat climate science. It just forces us to think in probabilities. And here's the twist. Chaos isn't just a problem. It's a tool. The same sensitivity that ruins weather forecasts can be used for encryption. Chaotic maps scramble data. A tiny change in the key produces a completely different output. If you don't have the exact key, you get noise. It's like the toaster dial again. Set it to 2.5001 instead of 2.5. The message comes out charcoal. Only the intended receiver knows the exact setting. Chaos also lives in your chest. Your heart is a nonlinear oscillator. Normally, it beats regularly, but sometimes it goes chaotic. Ventricular fibrillation is a chaotic electrical storm. The heart quivers instead of pumping. It's a deterministic system that has fallen into the attractor of death. Understanding that chaos helps doctors detect it, predict its onset, design defibrillators that know when to shock. Chaos theory isn't just weather. It's encryption, cardiology, population dynamics, turbulent fluids, and the stock market on a bad day. So what's the one thing to remember? The universe runs on rules, but those rules themselves hide the future. A rounding error of 0.000127 is enough to break a forecast, not because the math is weak, because the math is that strong. Sensitivity to initial conditions is not a bug. It's the shape of reality. The butterfly doesn't cause the tornado, but the math limits the forecast. The toaster dial has infinite precision in theory, and you can never set it exactly right. That's the nature of deterministic chaos, and now you know.